Welcome to lecture 19 of the course Computational Complexity. So we have been seeing complexity classes based on how much space a certain computational problem takes, right? So we have so far seen classes such as log space L and NL and co-NL and so on, right? So today we see another complexity class which is based on the space usage. So this is PSPACE. Okay. So what is PSPACE? It is just a space analog of P. P was the set of all the languages that could be solved in polynomial time, whereas PSPACE is a set of all languages that could be decided in polynomial space. So it's a union of D space n power k. So for all integers k. So maybe I can say k equal to 1 to infinity, right? So anything that can be solved in any polynomial space is in PSPACE. So as we have seen, just to remind you, D space of Fn is always contained in D time of Fn is always contained in D space of Fn. Hence, P is contained in PSPACE. What I'm saying is that we have already seen in one of the previous lectures that D time of Fn is contained in D space of the same function. Maybe I'll just move it around here. All right. So hence P is contained in PSPACE, right? So if something can be done in Fn amount of time, it can certainly be done in Fn amount of space, just because in one time step it can write at most one tape location. So the space usage will never be more than the time taken, right? Anyway, this P is contained in PSPACE. This is an easy inference. Some languages that are in PSPACE are, let's say, SAT, for instance. So why is SAT in fact SAT is in linear space? Why is that? Because given a particular assignment, you could have so there are n variables, let's say, right, and which means there are 2 power n possible assignments. We could have a counter of length n where we cycle through each of these assignments, and we try out these assignments one by one for the Boolean formula, and verifying a Boolean formula whether a certain assignment sets it to true or false is not that difficult. So that doesn't take any significant amount of extra space. So all the main idea is just this. So the space required is linear space. Similarly, maybe if you consider breadth first search, given a graph and you want to do the breadth first search, it's also linear space. So because the graph itself in adjacency list representation requires order n plus order m, where the vertices plus edges, and whatever is required for the representation of the graph is the time required, the space required for the BFS is linear in that, right? So BFS is also D space n. So this is not that difficult to see, so I am not going to elaborate further on them. And we have already seen that PSPACE is equal to n PSPACE, meaning if I had defined a non-deterministic analog of PSPACE, it is the same as PSPACE itself, right? So this is something we do not have in time complexity. P is different from, or we do not know whether P is equal to NP, right? That is a big problem, big open problem. But whereas in space complexity, PSPACE and NP-space are the same. Again, this is yet another example of things happening in space differently than how they used to happen in time. So why is this? This was because of Savage's theorem, right? So any polynomial, let's say NP space. So clearly PSPACE is subclass of NP space, but then take any non-deterministic polynomial space machine. You just square the polynomial, that is the space usage of the corresponding deterministic polynomial space machine. So it will just be square of a polynomial. Square of a polynomial is still a polynomial, right? So something takes n power k non-deterministic space, it can be done in n power 2k deterministic space. So if n power k is a polynomial, n power 2k is also a polynomial, right? However, the class log space is distinct from PSPACE. Why is that? This is because of something that we are yet to see called space hierarchy theorem. Right? So it is kind of similar to time hierarchy theorem. So what it says is that, so time hierarchy theorem kind of said that up to some logarithmic factors, if you have two functions f1 and f2, d time f1 is strictly contained in d time f2, right? Where f1 is smaller than f2, then d time f1 is strictly smaller contained in d time f2, meaning there is some language that it can be decided in f2 time which cannot be decided in f1 time, as long as f2 is sufficiently bigger than f1. Something similar we can say for space also. We'll soon see this the proof, not in this lecture but in an upcoming lecture. So here we have log space in the left hand side and we have PSPACE in the right hand side. So that's the distinction. Now let us define. So again, this is just some aspects about space complex PSPACE, right? So now let's define PSPACE completeness. Again, this is similar to, we have already seen two notions of completeness in this course, NP completeness as well as NL completeness. So this is yet another notion of completeness. Just like what we have seen before, it uses reductions. So let me formally define it. The first part is simple. B is in PSPACE. B is PSPACE complete if B is in PSPACE. Just like we said, B is NP complete if B is in NP. And two, every PSPACE language, every language in PSPACE, for all A in PSPACE, A is reducible to B. Okay, but what is the reduction used? Right. So in the case of P, in the case of NP completeness, we had polynomial time reduction. In the case of NL completeness, we had log space reduction. So what is the reduction used here? So one thing to note is that the reduction used should not be as powerful as the class itself. So we cannot say PSPACE reduction here, because then it would mean that if any A is in PSPACE, if you use PSPACE reduction also, then you might as well decide the A. You don't need a reduction to transform it into another thing, right? So in fact, in the case of PSPACE completeness, the reduction used is just what we have already seen. It is polynomial time reduction, right? So as of now, we think polynomial time is not, we don't know if it is as powerful as polynomial space reduction, right? It could be lesser powerful, but it could be the same too. That's why we find polynomial time reduction to be appropriate to use for this requirement. So it is something that seems to be less powerful than PSPACE, right? So again, we have already seen polynomial time reduction, right? Okay, so now this is PSPACE completeness. Now let us see a PSPACE complete language, right? Again, whatever I am saying, it is there in CIPSR. The language is called, maybe I'll just rewrite this. True fully quantified Boolean formula, or it's otherwise called TQBF. Okay, so what does it mean? It's a Boolean formula. However, in the case of satisfiability, right, or in the case of tautology, we also had a Boolean formula, but there the requirement was different, right? In the case of SAT, if I gave you a Boolean formula, you had to decide whether there is some assignment that sets the formula to true. In the case of tautology, the question was, is it the case that all the assignments set this Boolean formula to true, right? So one is asking, is there some assignment that makes it true? Second is asking, do any assignment, does it make it true? Both of these can be viewed as fully quantified Boolean formula, right? So what does fully quantified mean? Suppose there is a, maybe I'll just write this, right? Suppose there is a, suppose the n variables, there is a formula psi with n variables, right? Now a fully quantified Boolean formula or fully quantified psi is of the form q1 x1 q2 x2 and so on qn xn. So let's say the n variables are x1 x2 up to xn, and then psi, where each one of these q1 q2 are, they're all quantifiers. Quantifiers mean they could be existential quantifier or universal quantifier. There exists or for all. So basically, now what is SAT in this form? SAT is a fully quantified Boolean formula where we are asking, does there exist an assignment such that all of these are set to, the formula is set to true. So we could think of it as where all these q1, q2, etc., all of them are existential quantifiers, right? If all these q1, q2 are, we are asking there exists x1 such that there exists x2 such that there exists xn, right? Such that the formula is true, that is satisfiability. Whereas tautology is something where all the assignments, right, x1, x2, etc., all the assignments for all the variables set to sets the formula to true. So it's a for all situation. Maybe I'll just, so SAT is something like this: there exists x1, there exists x2, there exists xn, psi, right? This is SAT. So both tautology as well as satisfiability are TQBF, and if you think about it, we saw these languages called QSAT subscript K, right? So they were when we discussed polynomial hierarchy. So this were of the form, so just to recollect, right? QSAT 2 was there exists y1 such that for all y2 the formula is true, right? So where y1 and y2 are sets of variables, so there exists y1 such that for all y2, so these are sets of variables. Some formula psi of y1, y2, this is true, right? So even that QSAT, or sorry, this is QSAT 2, but similarly you can write QSAT K, just that the number of alternations will increase, but then all the variables are quantified, right? So y1 contains some variables, everything that is not there in y1 will be there in y2. So QSAT 2 can be written as a TQBF, and hence yeah, and anything QSAT K can also be contained in TQBF. So QSAT K or even QSAT K complement is contained in TQBF. They're all they can all be represented as fully quantified Boolean formula, which we are asking whether they are true or not. Right. So yeah, formal definition, phi is a true fully quantified Boolean formula, but anyway I have explained it. And this I have said this before, I will say it again. The order of the quantifiers matter. So it's not like if you swap the order or something else, the meaning is retained. Because of, let's say, integers, for all x, does there exist a y such that y is greater than x? Where x and y come from integers. Where x, y are integers. There is no, so whatever integer x is, I could pick a y that is bigger than x, right? So the first one is true. But there is, if you swap the order, it doesn't work because there is no y that is bigger than all the x, right? So there is no integer that is bigger than all the other integers. If you tell me a specific integer, I can always produce an integer that is bigger than that. But there is no integer that is bigger than all the integers that you can give me, right? So the second one is false. Again, this I have already explained. So TQBF is PSPACE complete. Why is this? So let us see why this is the case. Again, why is this the case? So there could be, what are the possibilities, right? So one is that there is no quantifiers, but TQBF means all the variables are quantified, which means if there are no quantifiers, there could be no variables. So this means it's a formula without any variables. So formula of only constants. So if it's a constant formula, it is something like the Boolean, like true or true and false, something like that. Right? Some just like a 3 plus 4 or 3 plus 4 multiplied by 6, some numerical equation without variables. It's just like a Boolean equation without variables, and one can easily evaluate that without much difficulty. So this is certainly in PSPACE. What if there are quantifiers? Let us look at the cases. So look at the first quantifier. There are two possibilities. The first quantifier is an existential quantifier, there exists, or an universal quantifier for all, right? So let us consider both. So let us say the first quantifier is there exists quantifier, existential quantifier. So it says there exists x1 and something else, right? Something else. So there could be other variables in this something else. Now, how do we solve this? So we want to check whether, so now the formula is saying, so some formula, right? This formula is saying, so this could be psi of x1, x2, something, right? Where the psi also contains quantifiers, or maybe let me just say phi of this, right? Where phi also contains quantifiers. It will have quantifiers because, so now we could set x1 to true and see whether phi is true, because everything else is quantified inside phi except x1. So if you set x1 to be true, phi becomes a TQBF instance, and you could recursively do the same algorithm. If you make x1 to be false, again phi becomes a TQBF instance, because the only variable that is not quantified in phi is x1. x1 is set to false, and the rest are quantified. So again it's a TQBF instance, and we want to check whether so the question is, does there exist in x1 such that phi is true? So you will check either is phi x1, is phi true, x2, x3, etc. Is that true, or phi, so phi true, x2, etc. is this true, or phi false, x2, etc. is one of these true, because both of them are TQBF instances. Now when the first, so again it's a recursive thing. The second thing is when the first quantifier is a universal quantifier. Again it's not very difficult. You could think of it as for all x1 something, but it's exactly what I described for the universal existential quantifier, except that now we want both cases to be true. So we will check both branches and check if both of them are true. So what needs to be done here? It is a recursive call. So at each instance, the tentative assignment of phi is x1 is stored, and then in the next level of recursion x2 will be stored, and the next level of recursion, the next assignment of x3 will be stored, and so on. So if there are m variables, right, m variables in this fully quantified Boolean formula, we need to remember order m variables assignment, so that is order m bits are required, and then finally at the end we will just make a we will just try to evaluate whether this is true or not, right. So we will just have an equation of constants, a Boolean equation of constants, which can be evaluated, and then at the end all these branches have to be combined. Like existential means there should, any one of the choices should be true. So all this can be done at the base, at the top level, right. So the space usage is order m because there are m items to be remembered at most, right. So again this is the high level idea, and this proof is there in CPSR. Read full proof in CPSR. Anyway, I explained the full proof here, maybe I just didn't write it down, but it is there in CPSR anyway, right. So this is the proof that TQBF is in PSPACE. So the space usage is order m, which is linear space, and this space is for all the recursion levels, not just one level, because at each level like constant amount of space is required to store whether x1 is true or that kind of thing, true or false. Now let's come to the bigger question, which is whether it is PSPACE hard, just like NP hard. We want to show that all the languages in PSPACE are reducible to TQBF. For all A in PSPACE, A should be reducible to TQBF, right. So it might help to recall some details of the Cook-Levin theorem proof, okay. So if A is in PSPACE, then this is going to be similar to that, but just that we wouldn't go to the details because we have already seen the details in the Cook-Levin theorem. So we'll just appeal to what we did then, okay. Okay, if A is in PSPACE, there is a PSPACE machine that decides A, right? There's a PSPACE deterministic machine, right? Now, given a string W, right, we can construct a formula such that W is in A if and only if that formula is in TQBF. That is a high level idea of the proof, right? This is how you do reductions, right? You want to show that given a string W is in A if and only if some fully quantified Boolean formula is in TQBF, right? This is what we want to show. So how do we try to show this? Okay, this is the goal of the reduction. The second point of the reduction is that the construction of the instance phi should be in polynomial space, polynomial time, right? Because this is a polynomial time reduction. So the construction of this formula should be in polynomial time. Okay, so how is that going to work? So as I already said, there is a PSPACE machine M that decides A. So W is in A if and only if M accepts W, right? So we will use M and W to construct this formula, right? Okay. So if M accepts W, that means there's a computation table that you can draw, right? We know it's a polynomial space machine. Let us say the space, let's say it has single tape. Let us say the tape usage is n power k. Okay, the tape usage is n power k. And what is the number of what is the height of this computation table? It is a maximum number of rows it can have. Each row corresponds to a configuration of the machine. How many configurations can we have before we start? If we see the same configuration again, it means we are looping, right? Which means we have come to the same configuration again. Again, we will come back to the same thing and we are looping. So what is the maximum number of distinct configurations that you can see? And we have done this calculation many times. It is the maximum number of configurations that we can have for a space bounded machine. So if we have an n power k space bounded machine, the number of configurations will be 2 power d n times n power k, where d is some constant, right, where and n is the length of the input. So this is like Cook-Levin theorem, but in Cook-Levin theorem it was time bounded. So the number of rows was n power k, and because the time was n power k, we said that the columns also will be n power k, the space usage will be n power k. But here it works differently, because here we first know that the bound on the number of columns or the space usage, and because of the columns are bounded, the space is bounded, we know the bound of the configurations, hence the time of the computation will also be bounded. It will be exponential in the space. Again, we have seen this d time or d space fn is contained in d time 2 power order fn, right? So it's the same thing here. Now again, this is a deterministic machine, right? So just like in Cook-Levin theorem, we can write a formula, Boolean formula, to check whether Ci or Ci plus 1 is a proper successor of Ci. A configuration I plus 1 is a successor of configuration I. We can write a Boolean formula for it. And this formula will be of size n power k. So given to check whether some configuration C is or maybe I'll just make it more clear here, Ci plus 1 is a valid configuration of Ci. Okay. So basically we need to check, we know the start configuration, right? Given a particular input, it's known. We know the accepting configuration. Again, we can do some things to make it, we can force the machine to have a unique accepting configuration. And we need to know whether there is a path from the start, or path meaning a sequence of configuration from the start to the accepting. And we know that the maximum number of steps that we can have is 2 power d n power k steps. So can this table have a valid sequence of configurations such that the first is a starting configuration, last is the accepting configuration, and every configuration is a valid successor of the previous configuration. Right? Again, this is exactly what we did in Cook-Levin theorem proof, just that in this case we are bothered about just that in this case, one is that we have a deterministic machine, so presumably the number of successors are less, but that doesn't really feature in the computation anywhere. 2, the number of rows are higher, right? There we have n power k rows, here we have 2 power d times n power k rows, which is exponential in that. Okay, now let us write a formula for this. So let phi c1 c2 t. So what we will do is we will end up writing a fully quantified Boolean formula for this. So we will use all the quantifications and that we want. So the goal is to come up with something. Generally we want to say, does there exist a sequence of configurations that takes you from C1 to C2 in t steps, right? So now if we can accomplish this, then we can set C1 to C start, C2 to C accept, and T to 2 power D times n power k, right? So then we can solve whatever we want. Okay, so let us see what is C1, C2, 1. Can we move from C1 to C2 in one step at most? Right? C1, C2, 1. So what do you mean by one step at most? Either the C1 and C2 are the same, which means 0 steps, or C1 and 1 step computation gives you C2, right? So either C1 equal to C2 or C1 to C2 in one step. And this is not that difficult to do because C1 equality can be easily checked. And C1 to C2 in one step, again, it can be checked by what we saw in the proof of Cook-Levin theorem. We had this phi move, which was essentially this, making windows into tables and so on. So both of this can be done, so that is fine. So this formula is of size, I think, n power k. or order n power k, this entire thing. So that is good. Okay. Now we want to see whether we can generalize this for not one step but t steps. So let us see, again we saw Savage's theorem. Let us see how to write this in t steps, because if you write in t steps, like if we do it like in Cook-Levin theorem, we will have to write C1, C2 is a successor of C1, C3 is a successor of C2, C4 is a successor of C3, C3 and so on, which will mean an exponential set sequence of such things. So which is 2 power d times n power k times n power k, which will be right. So we cannot afford to do this, to check phi C1 C2 1 and phi C2 C3 1 and C3 C4 1 and so on, because this will be exponential size. So we cannot afford to do that, right? So we cannot do that. So how do we do this more intelligently? We want to reduce the size of this formula. So what we will try to do is something that we tried in Savage's theorem already. We will use recursion. So if there is a weight from C1 to C2 in t steps, then there should be a middle point at t by 2 steps, t over 2 steps. Where were you? Let us say you were in some intermediate configuration called M1, right? So we don't even know what M1 is, but there may be some configuration called M1. So I could write, does there exist an M1, right, such that from C1 to M1 you can go in t by 2 steps, and M1 to C2 you can go in t over 2 steps, right? C1 to M1 in t over 2 and M1 to C2 in t over 2, right? So basically this is the midpoint of the table, right? So C1 here, M1 here, which is roughly at the midpoint, sorry, small m1, and C2 here. So if you can go from C1 to C2 in at most t steps, then this should be possible, right? Right. So now let's see what can be done. So now we could possibly repeat this trick again, right? So there exists M1 such that this is true. Now I could possibly rewrite this part C1 M1 t over 2 in a similar fashion by this red color stuff, and M1 C2 t by 2 into this blue colored notation. So this here and this here. Basically between C1 and M1 there has to be an intermediate M2, and between M1 and C2 there has to be an intermediate M3, right? So we are checking whether C1 to M2 can be traversed in t by 4, M2 to M1 can be traversed in t by 4, M1 to M3 t by 4, and M3 to C2 t by 4. That gives you this kind of formula. But notice what is happening here. I have split the original C1 C2 t into 4 parts, C1 M2, M2 M1, M3 M1 M3 and so on, and the t became t divided by 4, and it is, so now the t became 1/4 and we have 4 parts, but now this is expanding and expanding, and now this doesn't seem to be, and I think even if we try to unroll this t by 4 into single steps, this will be actually the original situation again. We will have an exponential sized formula without any size reduction. So this is not going to help, right? This is just some I'm just using recursion but not really making progress here. So the length is not decreasing here. So now, so this is whatever we had in Savage's theorem does not really help, but we now use a new trick called folding. So what does folding mean? We'll see now. So consider the top formula again. There exists M1 such that phi is C1 M1 t by 2 and phi M1 C by 2 t by 2, C1 t2 phi M1 C2 t by 2. Now I am going to write this in a new way. So instead of writing phi C1 M1 T divided by 2 and phi M1 C2 T divided by 2, I will just write it as, so there exists M1 here, there exists M1, same thing. I will write it as C1 M1 and M1 C2 are the two pairs, right? So I will define new two variables C3 and C4. Whenever C3 C4 are equal to C1 M1 and M1 C2, right? I will check phi C3 C4 T by 2. Whenever C3 C4 are C1 M1 and M1 C2, I will check phi C3 C4 T by 2. So when C3 C4 is C1 M1, I am checking phi C1 M1 T by 2, which is what we have the first term here. And C3 C4 is M1 C2, I am checking phi M1 C2 T by 2. Right? So for all C3 and C4 such that they are like this, they are in C1 M1 or M1 C2, I do this. Okay. So I am using their exists in M1 and for all C3 C4 in this set, right? So now I am using some new kind of expressions here, right? So I am using contains is a member of C1 M1. How do we write that in a Boolean setting? It's not very difficult. So what you do is you can have a this particular part, this blue underlined part can be rewritten by this part. Can be rewritten by this entire thing. So whenever C3 C4 is equal to C1 M1 or C3 C4 is equal to M1 C2, right? So this is M1 C2. This kind of looks like an E, but it is C2. When this happens, this implies that phi C3 C4 T2 T divided by 2 must be true. Okay, so the rest is same. Phi M1 for all C3 C4. Whenever C3 C4 is equal to C1 M1 or C3 C4 is M1 C2, phi C3 C4 T by 2. So now the first part is now the only thing that is remaining is the equal to symbol and the implies symbol. Now finally, I leave it to you to think how to write the equal to symbol and the implies A implies B and A equal to B. How do you write it in a using just Boolean formulas? These are very, very simple exercises. Maybe you might have seen this in the first class in Boolean logic, so you can think about it. This is not very difficult. So you can the point I want to impress upon you is that all this can be done in using Boolean formulas. So now the formula is something like this. Okay. So this entire formula is now some constant multiplied by n power k. Okay, the part after the quantifiers. Okay. Now again, phi C3 C4 T by 2 is something that we need to go deeper into. So how do we go deeper into that? Again, we will use exactly the same thing. I can define intermediate states C5 and C6 and the intermediate state M2 and then variable C5 and C6 such that maybe I'll just write it a bit C5 C6 is equal to C3 M2 or C5 C6 is equal to M2 is equal to M2 C4, and if when that happens, this implies phi C5 C6 T divided by 4. Okay, so this is how you expand out this quantity, the blue underlined quantity, phi C3 C4 T divided by 2. So now when I combine all this, so recall we were trying to write a formula for phi C1 C2 T, which we first wrote it as phi there exists M1 such that for all C3 C4 something, and the rest. So I can write it as there exists M1 such that for all C3 C4 there exists M2 such that there are for all C5 C6. there will be some formulas involving C3, C4, C1, M1, all this, and C5, C6, C3, all this, and then finally we will have 5 C5, C6 T by 4 as part of this, which again can we go deeper and deeper into. So the point is that each level adds only a linear, some constant multiplied by n power k, right, which is this is what I have written here in the part that I am underlying now. Each level needs extra space is some constant times order. So order size of C means order size of a configuration space, right? And we know the size of a configuration is order n power k, so it is still another constant, so it's still order n power k. This is the extent of memory required at each level, right? And at each level, notice that the t became t by 2 and then t by 4, right? So every level the t is halving, and we know what to do at the base case when t equal to 1, right? This is what we could do. This is what we did, right? So the base case is at 1. So how many levels are required to go from t to t divided by 2 to t divided by 4? So it is log t number of levels. So or the number, so the height of the, so I am saying log h here, where h is the height of the computational table, which is 2 power d times n power k. So log h is the height of the computational table, so where maybe I'll write that also. H is equal to height of computational table, which is equal to 2 power d times n power k. So when you take log of that, it is just d times n power k. So this is the number of levels, and at each level you require order n power k space. So the total space used is some constant times n power k multiplied by order n power k, which is order n power 2k with a constant. So it is order n power 2k. And this is the total space required to write down the formula. So this means that this is the total space required for the computation of the formula, and even to write down the formula, it's a similar amount of space, right? So this is the recursion length, and this is the number of space required, right? So hence, and the correctness is kind of evident, right? Because again, from our experience in the Cook-Levin theorem, this formula captures whether there is a sequence of configuration that lead a string to be accepted, which happens when the string is accepted by a machine, which happens when the string is in the language, right? So again, everything is if and only if. So the correctness of the reduction is evident. The time complexity is total space is n power 2k, and the time taken for the computations also, this is a very structured thing, that's also is polynomial time. So that's so just to summarize this, we defined what is p space, which is polynomial, it's in space analog of p. We defined p space completeness, again, which is a space analog of kind of a space analog of NP completeness, and the first p space complete language that we saw was TQBF, which is short for true fully quantified Boolean formula, where all the n variables are quantified. We saw that SAT, QSAT2, tautology, everything is in TQBF, everything is a sub problem of TQBF. And we saw why TQBF is p-space complete. The fact that TQBF in p-space is rather straightforward, and the proof that any p-space language can be reduced to TQBF requires us to go through computation table and some simplifications in the Boolean formula that encodes the configuration. And that is about it for this lecture. I'll complete the rest of the p-space completeness in the next lecture. I just wanted to add one more thing. So notice that we are doing this under polynomial time reductions, and we saw that SAT is contained in TQBF. Tautology can be represented as a TQBF instance. QSAT2, QSAT K complement, all of them can be represented as a TQBF instance. This means that SAT is an NP complete language. All of NP is contained in PSPACE. All of co-NP, tautology is a co-NP complete language, is contained in PSPACE. All of sigma 2 is contained in PSPACE, sigma k is contained in PSPACE, pi k is contained in PSPACE. So the entire polynomial hierarchy is contained in PSPACE. This is what it means, right? So think about this particular fact. So all of NP, co-NP, sigma 2, sigma k, pi k, all are contained in PSPACE. And with that thought, I think I will close this lecture. And in the next lecture, we will see a couple of more instances of PSPACE complete languages. Okay, thank you.